So good morning, everyone. Can you hear me and see me well? Please, in the chat, plus sign. And we'll start shortly. So can you see and hear well? Plus, not in general, but here. So in the chat, in the YouTube. So today gonna be really, I think, exciting, interesting topic, and next one even more interesting. So I think we are closing into most deep metric learning also is really interesting topic, and now it's starting to overlap with generative models. So it will be really I think so you can do a lot of things. So this is a kind of alternative way to describe many problems without actually knowing the loss function. Also, this is similar to also in the behavior and in results. It's kind of similar to the reinforcement learning, where you don't have really smooth looking losses, and you have really only the very sparse ground truth, like the score or the like a value function for some event, and basically it's and then the model learns how to behave or how to deliver you the results in the best way, just using very little interaction from the labelers or from the environment. So this will be really interesting. Okay, so I see only one plus. I really hope that others also can hear and see. Well, and then others more will look at this later, because later you also have to do the homeworks and stuff. It will be really interesting homework. Next one will be even more interesting, I think. So just a second. It says my videos stream right now is at very high resolution. And I cannot change it now. So seems, oh no, I can. Okay, let's reduce the resolution. Okay, if by any chance the video will start degrading, then let me know in the chat. So the models. We will do today two different GAN models. So the GAN models is generative models, so that will map some kind of distribution, random distribution or some informed distribution to actual images, which are these samples, or it could be also audio, it could be like sensor data. For example, if you want to generate a data set of realistic sensor data or something like that. And then you have the real world images. So you have basically two arms here. You have, first of all, like your data set of images. Today we're going to work with the extended NIST, right? So there will be, maybe I should illustrate it a little bit. Let me find some images. So we have extended NIST, right? These characters. So these characters go into the real data set, right? Then on this side, we have the distribution, random distribution, or it could be uniform, it could be Gaussian, it could be any what you want, or what you think is better. Gaussian distribution. Let me give you that example, what it is. So of course, many dimensions, right? Of course, similar, it could be also something more informed with some encoder or anything or something like that. So you have that part, like high dimensional vector, let's say 32 dimensions, 128 dimensions, so on. And the generator is the decoder. Basically, generator is the decoder. decoder, convolutional decoder. So that's why it's called DCGAN, Deep Convolutional Generative Adversarial Network. No, decoder, right. We will also look at Wasserstein GAN, VGAN, which is better. So this will be this part. Then we have real world images. This is the data set, right? Data set. Then we have 2 generated images. So this will be then, let's think how we will write it. Yeah, so this is not generated, sorry. So this is the real sample, X real. And this will be then X fake. Right, so let me see, can we find some more examples visually? What is this? Right, so initially the outputs will not look really great, right? So initially, as with all of these models, the outputs might look something like this, whereas the real sample would look something like this. Just a second. Something like this, right? But there is also one caution here, really important to understand, that there is no actual link between right now between this and this. So instead, like even right now there is the comparison between two numbers 8, right? In reality, maybe we should not even put it here as that, because in reality they would be just some different kind of letter there on the other side. It's not the GANs originally, like the generative adversarial networks. They are not meant to do the style transfer. So for the style transfer and like some kind of logic behind the latent variable will be something we will do next week. So that is even more related to deep metric learning. So here in this case is just generating any realistic sample from the latent variable z. So let's call this a z as well, right? And they could be like any kind of letter. It's just by changing z we would get all possible letters, all possible outputs. They would not be anyhow related to one particular letter. So that is that part. Then here there will be convolutional encoder, right? Maybe I should write a decoder. So convolutional encoder, and this guy will be just creating one output. So this will be just one scalar output. We can write batch, comma 1, right? And this will just predict probability. Originally, DCGAN would predict probability of the sample being real or fake, right? So that will be used by the discriminator, and it will just have the probability. For example, if this is a real sample, then I have 100% probability that this is a real sample here in the output of discriminator. If I give the fake sample, which is randomly sampled from distribution here, then this would be a fake sample, and the output should be 0. And then, of course, we should use some kind of loss. Of course, one thing that comes to the mind is just binary cross entropy. But to actually train this, we don't really need full binary cross entropy. You can use it. I mean, there's so many variations of GANs. It's possible to use binary cross entropy. It's possible to use all sorts of other loss functions. Even today, we're going to look at really interesting loss function that's on the Wasserstein GAN. But basically, yeah. So that's about this part. So then, how to actually train it? So the product, the actual product, what we want to create is this generator. So again, this is really similar to the proxy NCA loss for the deep metric learning, where we have some kind of model which is not used for the production. So here this is for the production, and this is just for the training. So the discriminator or this encoder is just for training. Right. And so the loss function, as you see, comes on this side. So it means that the generator gets trained only by discriminator. So that is what I meant by saying that in this case we don't need to know very precise loss functions, because for different tasks which we want to give the generator, we will use just the loss function which will come through discriminator. So we will train this guy like this. So the backdrop, the error gradient will go from this side to this side. And we will also have another loss which will go again from the discriminator, but just directly out to the real part. So we will have two losses, and these two losses are generally called, one is generator loss, another one is discriminator loss. So the generator wants to fool discriminator by feeding in fake samples and pretending that they are real samples, whereas discriminator wants to better discriminate between the real and fake samples and just always classify real samples as real. And so they are always kind of fighting with each other. That's why they are adversarial networks. And yeah, and then we will go to the loss function shortly. So let me just know in the chat, is this clear so far? Is this clear so far? Plus, minus. If something is not clear, please write some question. I will try to answer it. And then we will look at the loss function itself. Okay, I don't see response in the chat, which is not good. Okay, thank you, somewhat clear. Okay, that's good. We'll move on, and you will see the code, you will see the loss functions, and then it should be clear. So originally the paper, which was it? Original paper from Ian Goodfellow. So this is a really important name in the GAN, and also other. I think it was also related to some cyclic CTC loss or something. So the Ian Goodfellow is one of the most important researchers in this field. So this was from 2014, first GAN kind of paper. And in this paper, we will see that you have this this layout of the loss function, which again, this is one of those examples where you want to show some kind of similarity with parallel math fields, where actually this similarity is not very directly applied. So here this is a min-max game, two-player game. One tries to minimize, another one tries to maximize something, score, right? So G and D, the generator and discriminator. Generator wants to fool discriminator, and discriminator wants to be smarter. So, but then in this kind of loss, quote-unquote, description, it would be fine for the discriminator, because he wants to discriminate, give the highest probability for the X samples and give the lowest probability for generated samples, which are G of Z, this is the fake sample, passed to the discriminator, and then 1 minus, this is like opposite probability, right? So for the D, this makes sense. For the G, this is a bit tricky. So for the G, they want to do the opposite. So this part makes sense for G. This part does not make sense for G. And I think in general, I don't like, so this is a peer-reviewed paper, really important paper, but still like to just, so why would you, there is actually no like direct link between X and G. So it's, maybe you could create some link, but anyway, so this is not something that is actually done. So, but luckily, the same authors also give the real way how to train GANs, the proper loss functions. So the upper loss function is exactly the same as in min-max game, but for the GAN, it just drops the first like unusable term and just use it as that. So basically, the idea is that you have two losses, and these two losses fight each other. So one is trying to give a higher probability, so probability of 1 for all of these X samples, which are real samples, right? And give 0 probability for all of the samples which are fake samples here. So this is the discriminator loss, and then there is also generator loss, which tries to do opposite. It tries to fool the discriminator. So, and here is really important thing, which we will also code, is that they cannot update gradients like from. So if I'm trying to fool the discriminator, I cannot just update the discriminator gradient, because then it will not make sense. So I will just copy a couple of these equations and explain them again. So first of all, the generic equation, which is not that good. Then a little bit more specific. I could imagine that sometimes even researchers could just leave that equation and then say, oh, everything is working, and not even bother to explain that it's not actually usable. So anyway, here there is the what I was telling. So if I'm updating the discriminator loss, then there is again very important small thing here. So this thing is very important, that it's only updating the discriminator part of the parameters, and this is only updating the generator part of the parameters. So it means that even though the loss function goes through both models, G and D, in this part of the loss update, it only updates the D part, and in this part it only updates the G part. There is also another interesting part, that there is these kind of steps for repeating the discriminator loss more times than the generator. But it's also really strange that even though they add the steps, they write, we used K1. So we didn't use the loop here at all. But basically, at least for the basic implementation that we will do now, I don't see reason to add the loops, only if the discriminator is very weak. Maybe then the loops could help. But there are so many parameters that are very important in GANs. I will try to explain some of them, but there are many things that they're tempted to do, like for example, do different learning rates, or add these kind of loops and try to, I don't know, like control the flow of the loss by not learning one thing and learning other things. So, but all of those things are kind of dangerous, because they usually do not result in better results, but they just like mess around with your head, and you'll lose a lot of time with that. So, but I will show step by step some of the things. So that's about that part. So let me then give more examples. So I had some images which I forgot in the beginning. So the models themselves. I think you should be able to implement something like this, right? The like just the vector, which is then mapped to some kind of arbitrary dimension. For example, batch. If I have batch 128, the z vector, then I'm mapping this to 128, 1, 1, and then I'm at the end getting out my actual image, which is 1, 28, 28. In this case, if it's a RGB color image, then this is a 3, right? So, and instead, and for discriminator, we have almost the same thing, just the opposite direction. So at the end, we should get out something either with average pooling or some other technique, something which is like this, and then at the end, we just get b, comma 1, right? So b is batch, of course. So that part. And the loss itself would look not anything like really nice as we saw in this course so far. It's more like in the previous course with the reinforcement learning, where so in this case the generator loss is the orange one and discriminator is the blue, but it could be well other way around. There is like almost no guarantee that the way how these plots will look like. They might look something like this, and then like starting cycling, and then one is just going down and other one is going up. But the one thing is that what is really bad, which often happens, is that discriminator loss gets 0 basically. It kills the discriminator, and then basically it's you cannot learn anything. So it's often happens like that. And one of the reasons why it can happen like that is that the discriminator is too powerful. So I would say that one of the most important things about these GAN models is the amount of parameters. So key factor, number of learnable parameters, or basically layers, whatever. So basically, if you would use, so what the good situation, good combination would be not too powerful, not too large, basically large D, but as large as possible G. So if G generator, if this one do not have a lot of parameters, so it is very easy to make weak generators by just like upscale, have a 3x3 convolution, upscale 3x3 convolution, and you end up with like a few thousands of parameters or hundreds of parameters. Then it will not learn anything good ever. So that it should have like hundreds of thousands or millions of parameters just to do something reasonable. So, and then for the discriminator is exactly opposite. So if you just use pre-trained DenseNet 161 or something, and the GAN is much weaker, it will destroy GAN. It will destroy generator immediately. So it will just go to the 0 loss, and this will have no chance. So the parameters thing is really important. So I think there's also other things that are important, but parameters is I think more important than just fine-tuning the learning rate and other things. So that's about this part. I understand, right? Oh, you see something is happening here. Jamboard isn't able to load images. Oh. I really hope that it's now working. Anyway, so now let's go to the code. So I gave you the template already. So this template is 5.2. So let's start implementing stuff. I have few to-dos here. So one to-do is for the discriminator, one other one is for GAN, right? For generator, sorry. So discriminator should be just right amount of parameters, just right amount of complexity. Actually, we could also measure the amount of parameters. Let's do that as well, just in a second. So let's then start coding it. I could give you as a task to code it yourself and then wait. But I think like I don't just want to sit around, and I think like I really hope that you can do this, but might be chance that there's somebody could not do this. But so I will just show you the one option, and then for the home you will have a different kind of task. Well, you need to do the GAN for different data set, and with some additional updates which improve the convergence. Actually, they not converge, but improve the training procedure. So let's try to write then here. So self encoder. This will be just the encoder part. Torch and sequential. So this will be then torch and conv2d. In features will be 1, out channels will be 8, kernel size will be 3, stride. That's all. Let's use the typical configuration by not changing the width and height at all. So this is the typical configuration, right? Then torch and n patch norm. Again, you can use different norms if you want, but be careful. I would suggest let's start using this fixed architecture, because as I said, the parameter count is so sensitive. It's super easy to make nothing work at all just by changing the architecture. So, but it's also possible to create excellent results. I forgot actually. So just a second, I will share some additional information. Why actually these GANs are so good? But I think you already know that. So there exists this page, right? Let me share quickly back to the Jamboard. The GANs are basically not using any kind of losses like mean square error or anything like that, and that is one of the reasons why it can generate crazy good quality. So they could kind of invent, discriminator can invent better loss functions than human can invent. So there is these kind of GANs, like there is the, oh it's funny, they are advertising their own paper here, style GAN 2. I need to check that out. So that looks good. So anyways, so here is the site which is called "This person does not exist." So you should check out this site. This person does not exist. And this site is, every time when I refresh, generates new image of a person which is generated by GAN face, basically, which is not existing at all in reality. So you see these GANs, the quality is great. Like I think it was NVIDIA paper which did this. I'm not sure. So this is some, I think, new paper, because I think it's not related to style transfer generating these things. Okay, why it's so slow? Anyway, so you can play around with this site. So this person does not exist, and this is one of the reasons why we are talking about GANs, because GANs can create much better quality output than any other type of generative models, like for example variational autoencoders, or what was else there, some energy models. I think there will also energy based models. So anyway, these are NVIDIA paper. Let me just go over quickly. Okay, I don't want to waste time. Okay, I will look at this later. So I think it was just the advertisement for their paper. Okay, so that was just a small side note, because I forgot to explain actually why it matters. So why we are building GANs instead of doing some other types of models. Okay, so let's keep writing the model. Then the next line would be some kind of loss, some kind of activation function. In this case, let's use leaky relu because theoretically it cannot die, but practically I have not seen good explanation. But in general, even the relu, which is prone to dying, the simple relu, which can die really fast, still works really well in deep models. And for a long time, people have been trying to invent other activation functions, and still the just simple dumb relu works better. So stride 2, padding 1. Okay, so this will be this. So this will reduce the resolution by 2. So at the end, we will get the batch for 14. The input was 28, right? So this is the first segment. Then you will just copy the same segment again and change few numbers. So you will need to copy it 3 times. So this GAN will have somewhat a number of parameters, but as you see already, they will not be super smart. So it might be necessary to add more if the result is not good enough. So the easiest way how to add more parameters, by the way, the most easiest is just adding more channels. And so the channels or layers are your two options. So the channels is much easier, of course. So 32, 832. So then we will reduce the size to the batch, 32, 7,7. And finally, let's move from 32 to 64 dimensions. 32, 64, 64. Relu, maximum, and then at the end we will have the batch 844, and then we could add more layers, but let's then just add the torch NN, adaptive average pool or adaptive max pool if you're already using max pools. So just to have the out size of 1 by 1, and this will produce the output of batch, or not 8, but 32, 64, sorry, 64, batch 64, 1, 1, right? So this is nice. Then we will add the classification part, right? So this will be then, let's call it just multi-layer perceptron or whatever, like they usually use that notion, even though that's not correct. So torch and then sequential in features, torch and then linear. So this will be linear, in features will be 64, out features will be 1, and then finally torch and sigmoid, because this type of model will use logarithm in the loss function, which is used as it would be the probability distribution, right? So it should not then produce something which is outside of the bounds from 0 to 1, right? So the 1 is 100% and 0 is 0%, right? Finally, we need to add few lines here. So this will be then the encoded, so X encoded, self encoder X, just with the forward, not because without calling forward, this is unreadable code. It's really not good way to do this. So Y, so and then this will be, yeah, this will be Y prim. Right. So about that, don't think we except we need to reshape the stuff. So the easiest way to reshape it is just calling then X. X flat, X encoder. Flat, the easiest way is just calling squeeze. Squeeze. So this will reduce from batch 64.1.1 to batch 64, right? Then we call this enc flat like that. That's about it. I hope I don't have mistakes. I will drop this to the Jamboard. Slide number 4. So this is the discriminator, and while you are catching up in the Jamboard, I will just check the amounts of parameters. I will drop that code as well so that you will be able to also check your amounts of parameters. So we'll just move this a little bit up here, but it doesn't, I could also leave it here, it doesn't matter. So let's then make some function to print out the amounts of parameters. So def get param count. So then this will be model. So for the model, to do this, the one way how to do this would be, let me think. So the size of parameters, this will be that. So let's see. So list model parameters np params np array. Maybe I could do that even without np, but let's use it np. So then parameters, then I will need also to use it to the CPU, except I don't like that. I'm calling this on here. Might have problems later. Okay, anyways, let's keep it like that. So that part, then hopefully I could, but it will not work like that, unfortunately. Okay, let's keep it then first list, and then second part will be other part. List. This will be just params for param in params. Okay. NP, or maybe I could just use the size now. Oh, yeah, then maybe I should even not use the CPU. So there will be then the count param will be np prod of param size. I hope like that. So the product is just like, I don't know, like taking the size 0 multiplied by size 1 and so on, because they are matrices basically, and so that is that. And then let's say add here the result. Result will be plus count param, then return result, and then we could print out here, print the, so let's write it f model d params. How many are there? Get params. By the way, this code which I'm writing now is optional, so please make sure that you write discriminator code. This code is not like, you don't need to write it immediately now. So you can, if you want to write it, but it's not necessary. So it's just for validation purposes. So if I run it, okay, I have 20,000 parameters, which is not a lot, but yeah. So, but if I would use the pre-trained, Yes, great. Thank you. I see in the chat, Matisse also confirmed this. Yeah, so this is not like hundreds of thousands, but as far as I know, this works good. But if I would use the pre-trained DenseNet or ResNet, even ResNet 18 or something like that, I think it will have much more parameters, and then it would not work with the generator model, which I have in mind. But of course, if you increase the generator model, then you should also increase the discriminator. But they should not be like out of balance totally. So, but we will see that. Anyway, we will see that. So the discriminator code has been given in the Google Classroom. I also dropped the other one, which is optional. So let me know in the chat, is discriminator ready? Is discriminator ready? So plus minus, if you're working on it, then maybe W. So let's see that Matisse has done it. What about others? So let's wait for more confirmation. Then we will do the generator, and then we will do the loss function. And that's about it for the DCGAN. Then we will move it to the Wasserstein GAN, which is even cooler. So, okay, I see one plus, so I assume, okay, we have at least 3 people already, so that's great. So let's then move to the generator, right? Again, all of these models can be made as you want them to be, but I suggest you start by my configuration. As I say, they are super sensitive. It's very easy to make them not work. So let's think. So we will need to have some initial size. Yeah, let's scale. So initial, so I mean not initial, but how we could call it, the decoder size. Decoder size will be input size divided by 4. So because we will have 4 upsamplings, I think we have 4, 1, 2, scale factor of 2. Let me think. We will upsample once. Okay, we have, I know why we have 4, because we will actually upsample it twice. Upsample twice by multiplied by width and height. So by 2 extra dimensions, which are width and height. That's why we will have 4. Okay, so that will be fine. So we'll do that. Then also, we could just immediately start building up the convolutional network, like fully convolutional, right? But again, there is this serious problem with number of parameters, and one of the easiest ways, again, how to increase the number of parameters. Also, maybe we should do this here. Let's increase also some, okay, no, I will not increase. It's so easy to break them, but basically you can add here some extra linear layers between the non-linearities, and that will like increase parameter count much better. So I mean, like here you need to write a Y layer with all of the transformations. So here you just can add a few linear layers, and that will increase the amount of parameters. So here we can do the similar thing in opposite direction. So self MLP multi-layer perceptron. Then here let's call then. So again, let's create some structure which can be improved later. Sequential, torch, and then linear. Yep, let's call it like that. So then there will be Z size, which is the input size of the embedding. That is that. Then we will have what will be our initial size, so self size decoder size squared, and then finally we will have the white square. Okay, yeah, right, it's squared like that. So then finally we will have the in channels. So the first in channels, let's call it, have it 128. So that will be that part. So then self decoder torch and sequential. Okay, so let's start by torch and batch norm 2D. Norm features 128. Then torch and again, the way how it's right now written, it could be written any other way. It's just some structure which works. When we have something working, then you can change to other structures. It's definitely can be improved. So, and by the way, the NVIDIA paper also uses the upsampling, not the transposed convolutions. So transposed convolutions with these kind of internal paddings can be used, and this will be working as well. But the upsampling, at least from their paper, seems to give much better results visually. So that is that. So then again, let's use the common convolution, which do not change the size. In channels 128, out channels 128, kernel size 3, stride 1, padding 1. Okay. Okay. Then we can add again torch and n batch norm. Okay, are you building GAN or DCGAN? So as far as I understand, the DCGAN, deep convolutional GAN, is basically a little extension of GANs. In their original paper, as far as I remember, the primary kind of like addition to all of this process was that they wrote the architecture of the convolutions, and they also gave the vector arithmetics examples. So in the sense, just the original GAN and DCGAN are not that different. I think they are the same. Basically, there are basically some minor differences in the architecture, basically, and also they are usually found by the term DCGAN, the deep convolutional GAN, but GAN is more generic, basically. GAN you can use also, like term GAN, you can create a GAN for audio generation or something like that, so generative adversarial networks. So this is DCGAN in the sense, in the quotes probably, DCGAN. So I cannot, if you know like some serious difference between the original GAN paper and DCGAN paper, you can point it to me, but I don't think there is big difference. So that is this. So batch norm. So in features, so norm features will be 128. Then torch and leaky relu. Okay, I hope that it will work just like that. So leaky relu. Okay. Hope it will be enough. Okay, we'll see. If by any chance this will be too weak, I will add some extra layers. So leaky relu, right? So then we will do again the upsampling like that. Only then we will change from 428 to 64. Yes, that's a good point in the chat. Stefan is writing. Main differences was in the terms of layers. All linear layers and max-pool layers were placed with more convolutions to increase the depth of the net. So yes, the architectural change, not I guess in the loss functions or in the kind of any other mechanics necessary here. So that's why I'm still referring to both of them with the same kind of notation. So 64, then okay. So let's have this part. So then we can try to, from the 64, we can do to the 32. 64, 32, 32. Okay, and then finally, have already batch norm. Yeah, maybe I should actually do again the batch norm. So for 32, from 32 down, and let's do it gradually. So from 32 down to 16. 16. From 16 down to 8. And then from 8, I think we can go down to 1. So from 8 to 1. Really hope that I didn't mess up some kind of dimensions here. Thinking that's all right. Okay, so we'll zoom out a little bit. Copy this to the Jamboard. There is a chance that I have some bug here, but if I have, we can fix it later. Or you can point out to me. So I will copy this in the slide number 5. And the bottom part now, the execution. So there will be the Z flat from self MLP, which right now contains only one linear layer, but you could add more if you want. So Z, but again, if you want, if everything works, and then later slowly add more. So that's other thing. So then the Z2D, two-dimensional. This will be then the Z flat view as the Z size 0. So this means the batch dimension size, because of course if I would use this for the production, I don't want here to hard code the batch size. So 128 by the self decoder size, like that. Fine. So that will be fine. And then finally the y prim equals self decoder forward Z2D, right? So this part should be also fine. We'll drop this to the Jamboard. And then, okay, let's first of all check the parameter count. So run. Okay, so we have, maybe I've done this too much now. So I have 1 million parameters versus 20,000. Might be that I made it too many parameters. Maybe I should at least have 1 to 10 ratio. So let's, I think it should work also like this, hopefully, but I will add maybe a little bit more, not layers, but here the fully connected stuff for the discriminator. So the one quick hack would be adding here 64 by 64, then torch. By the way, I don't like it that there was not any batch norm or anything. So NN batch norm 1D num features 64. Here let's add leaky relu. After that again the batch norm. Okay, so I will check the number of parameters, and then if it will be better I will, oh no, right, the dimensions are not high enough to have any effect of these things, so just be 64 by 64. Yeah, maybe I need to then increase a little bit more or add more layers. Or maybe I can add here just expansion. I don't know, like let's expand it maybe to 512, and then reduce it back. Oh no, I don't like it that it's such a huge drop here. Yeah, I don't like this at all. But I guess I need to add one more layer. 4 by 4, I could reduce it to 2 by 2 probably. So I could add maybe one more layer here. By the way, you can leave it as it is for you. Okay, let's not start changing anything around. So let's leave it as it is with million to 20,000 ratio. Yeah, let's leave it as it is for a while. If by any chance this will not work, we will know where the problem is. So the discriminator is too weak. But if the discriminator is too strong, then it's much worse problem. So anyway, so I will comment out this thing, exit. So that, okay, so the next thing is we need some kind of random distribution where we, or some, I know, like with some kind of prior, we can choose whatever distribution we want. So we need some distribution from which to draw the z samples, right? So let's call this then distribution z. This will be torch NN distributions. Oh, why you don't have it? Oh no, torch distributions. Normal distribution or Gaussian basically. So then the mu value will be 0. The sigma standard deviation will be 1. So this will produce something in a range from -3 to 3. So I'm copying this part. Oh man, did not copy it somewhat. Okay, moving this to the Jamboard. Okay, we have decoder, we have this thing. Okay, so let's wait before we start building loss function. Is it done so far? Plus, minus, or working with it. So please let me know in the chat. And as soon as you're ready, then we will move on to the loss function itself. And if necessary, we'll improve the discriminator, or you can do it yourself even, because I think you know how to do this. I see 1 plus, let's wait for others as well. Okay, 3 pluses. Okay, so I hope we're good to go. Okay, 4 plus is great. So then we only have the loss function left, which is a little bit tricky, but not too complicated. So the tricky part basically is only to make sure that we don't mess up the discriminator or generator by updating wrong gradients, because right now we're using the same optimizer for both of them. The easiest way maybe could be just create two optimizers, which we will create a little bit later. But now, if you're using just one optimizer, it's, well, maybe we can even stick with one optimizer also for later. Let me think. No, I think we should have two optimizers for Wasserstein GAN if we are using some loop there. So anyways, but for one optimizer, it works great. It's just there is this thing that needs to check that you don't affect the inside the loss D, G, or inside the loss G, D. So, but it's no problem. We can do this. So let's write it here. So first of all, let's then sample Z. So Z will come from the distribution Z sample, and then the shape of the sample. So that will be X size 0, which means the batch size, and then Z size, right? And then also we want to move this to device. So this is our Z samples. Then let's start in the equation. It started by discriminator and then generator, but I suggest that we first start with the generator just to make sure that the equation stays so that we don't mess up the generator in the discriminator part of the equation. So it will make sense just in a second, hopefully. So then X generator will be more. You can also change the order, but then in that case, probably you should have two optimizers. So in general, I think one optimizer is better because then they are both in the same kind of parameter search space. So ZGen. So let's then call them for param in. So this part will be very important. We will try to disable now the learning of the model D, because model D will be used just for generating the loss for loss G. So whenever, maybe I should actually write it first and then explain. So let's write it first. So G generated. So this is generated. This is a fake or real? So forward X generated. So here, let me write down a few things. So this is the fake image. Then this is the is fake real. And for generator wants G wants this to be 1. So this is what it is. So then loss G equals the minus torch mean of the torch logarithm of YGAN plus epsilon, like that. So that's from the equation. So it's trying to now get that this output equals to 1. But there is a problem now, because the YGen goes through model D, and model D is something we don't want to train with loss G. We only want to improve the loss G. So here, want to improve G, do not want to change D. So, and the only way how we can lock that we don't change the D is by disabling the gradients for the D. For param in model D param. The other way is actually using other optimizer. So param requires grad false, like that. Oh, that's about fine. Right, so this part is done. So this is the generator loss. So then the discriminator loss. Again, we could use the same Z as for the discriminator, but it's always better to sample again, just to make sure that they are not directly mapped to each other, and then they would fight to each other just in this for the same Z sample. To be better if it fights over the whole distribution. So Z again, sampled again, but it could be also left as it is. It's just better working with again sampling. So that will be that part. Then here let's write again X fake. So this is not now the generator thing, but this is for the discriminator. So model G forward Z. Model G forward Z. So now in this case we need again to enable parameters for the D, because now we want to learn actually D, not learn D. So that is that part. And then the Y fake equals model D forward, and here goes again really important thing. I will actually highlight few parts which are super important. So here super important is to call detach function. I think we already talked in the reinforcement learning. So detach function will remove gradient, any gradient at this place. So basically we will not pass the gradient through the to the G. So if there is the X fake detach, then do not learn X fake detach, basically not if, but makes optimizer not appetizer, optimizer not learn G. Basically, it will detach the gradients at that moment in the functional graph. But it will learn the D here because this part is now enabled. So the detach is super important so for this case. That is one. Then Y real is the simplest thing what we can do at all. Like there's nothing more simple than Y real, which is just passing the real data, which comes from X, directly to the discriminator and get out the Y real. So then loss discriminator itself becomes again really simple equation from the slide number 2, I think. So torch mean of so the first part is torch log of Y real plus epsilon 1e minus 8. So the first part is clear. Basically, it tries to have 100% probability. So one will probe that real is real, right? And then it wants 0 probe that fake is real. So the other one, torch logarithm of 1 minus Y fake plus epsilon is like that. So that's about it. I will try to run it quickly if I don't have any bugs, and then I will share this also to the Jamboard and highlight few parts of it. It seems to be working for me, hopefully. So let me now share this to the Jamboard and highlight few parts. Yeah, it seems to be working. So I'm sharing this to the slide number 6. Now I will also highlight few very important parts, which are these gradient operations, basically trying to make sure that it's not learning things it should not learn. So here so let me actually share the slide. So here it's trying not to learn parameters D. Here also oh man, why did this happen? So why can't I draw over the image? Okay, now I can. So this part also super important, and this part also super important. So basically, these three parts very important to make sure that this works correctly. Also, the order right now is important, because if I would switch the order, then the discriminator comes first and then the generator, then again the gradients I think will not be correct. Because in that case, first of all, this will be enabled, then it will be disabled, and I'm worried that if I would put this the second one, then as soon as I call gradients false, it might mess up my previously defined gradients. So that's why the order also very important in these equations. So now I have this loss G, loss D, and then finally I just plus them together and backprop them. That's about it. So I will now upload my stuff to the GPU server. You can also train this on the Google Colab, of course. So let me see. So I will try to run this on the GPU. So this is 5.2 task DCGAN live. So initially it's generating the, okay, wow, I forgot one important stuff. So there is a bug in my code. It's not like super critical, but at the same time quite important. So let me show. So the bug is in the architecture. So here, when I generate the convolutional output, it should at the end have torch and n sigmoid, because my image is always from 0 to 1. If I would have original paper use tan H because it has the -1 to 1, if you want, you can also change the pre-processing of dataset to have -1 to 1, but make sure that generator have at the end sigmoid. The generator must be at the end sigmoid for this dataset. Otherwise, it will start generating the values outside of the range of 0 to 1, which the range is good because right now it's coming out from the dataset. So the dataset right now is producing images of those small letters, but those letters are from 0 to 1 range. So let me see. So I will drop in the update, the slide number 5. My small bug, unfortunately. So I hope that will be the only bug, but I cannot guarantee. So run it again. Oh no, I did not upload it. Okay, so upload, run. Let's see. So now it seems to be working. We'll update you shortly how it's doing. So now I added the sigmoid at the end to the generator, which was missing. Now I'm here, and now I'm looking at the results. So we'll see what we get. For those of you who have GPU, so that you're very lucky. Others can use the Google Colab. It seems to be working, hopefully. So I will show you the outputs after 35 epochs. By the way, of course, we don't have test dataset, right? Because how can you test the GAN? So there is actually active research direction to establish the best way how to evaluate if the output of a GAN is good or not good. So this is something you can also do your research on. So here there will be the outputs, so you will see. So after 40 epochs, we get already really nice letters. So I think the original selection is just 3 letters. So it seems to be O, C, and Z, or something like that. So you can change the parameters and have more letters included if you want. So actually, then I will show you after 77 epochs how it looks like. So after 77, it looks something like this. Okay, now let me write in the chat, is this working or not? So let me working, is this working, plus, minus, still working on it. And then we will go to the other part, because you already see that the loss do not look good at all. Like the loss plot is just like a mess, right? It even don't go in the same direction. So the kind of the generator is went down. Discriminator basically initially discriminator went down, then discriminator went up, then generator went down. Then basically they are both start like having equilibrium at some arbitrary point in the space, like in the loss space. So it's not like that there is any kind of normal terms of convergence. Maybe you could say that they are converging about some arbitrary values, but they also can just start diverge at any moment. So that is what we have here. So it's a Z, G, and Z, Z, O, and G. I think those are my letters. If you change the parameters, your letters might be a little bit different. So I just selected 3 letters with 1,000 samples of each, I think, something like that. You can change the parameters and have different kind of configuration if you want. Or you can change the data set, which you will have at home. So anyway, so you see it works, so basically. Okay, I see 2 pluses, so that's good. Let's wait few moments more, and then we'll move on to the Wasserstein GAN. I still don't see more pluses. If there is any like buggy stuff, please let me know. Okay, I see only 2 pluses, so I assume that others can catch up a little bit later. So let's keep looking at the outputs of the here in the Google Jamboard. Okay, so I can explain a little bit more regarding the next part of this session. So there is this problem of the loss what we just observed. So the loss is kind of is very chaotic. There is also really one thing which can be which can have significant problems. Is just called mode collapse. The mode collapse happens primarily when you have even weaker discriminator, probably. So or even so, it's actually can happen in both ways. Even if you have very strong discriminator, you also can have mode collapse. So if the balance is kind of off, then what happens is that they will just start predicting the same output always, and there is like 1 pixel change. Maybe I should try to find some mode collapse example. Let me see just a second. GAN mode collapse. We could make mode collapse ourselves, but I don't just want to so it's again too experimental stuff. It might work, might not work. So just to show you what the typical mode collapse, how it looks like. I don't like it. Probably one of the ways. This is not definitely the only way how this could happen. And by the way, the most likely it would just be always ones. So the mode collapse is something like this, that the GAN will start producing always just the one type of output, and basically all of the other types are somewhere like collapsed down. And basically the thing is that usually what I have seen is that actually they are not just producing one type of output, they are actually always they're producing something which looks exactly the same. So here there you see some variation, but normally this looks exactly the same. Maybe 1 pixel is changed, and that's enough to kind of satisfy the loss function. And basically it's not anything remotely like visible to the human being. So maybe this example is better. So kind of mode collapse. So that is something which could easily happen with DCGANs, and mostly happens when there is something out of balance. Either parameter count is out of balance too much. As you see right now, we already have 20,000 versus 1 million. So the more parameters for the GAN, the better. But for the discriminator, if we're starting to add more parameters or too little parameters, then some unknown balance, right? So then it will start collapsing to the mode. So that is that, and then in that case, when it collapses to the mode, then it's basically vanished gradients. Then anything you start to learn, nothing helps to get out of this situation. So then it's just like some vanishing gradient position in the space. So it's given here as an example from the WGAN, some kind of paper, I think. So density of fake samples, density of real samples, and then the GAN discriminator ability to detect the fake samples is only in this. So this is generating only small kind of like distribution on one end. So normally they should overlap somehow. So and then here the VGAN. So the VGAN discriminator. So it's right now written as the critic, but it's actually a discriminator. So it has the gradient which goes forever. So there is a really serious issue here. So this issue is following. So with the discriminator, you see that this would be some kind of probability here, and these would be like x inputs. So, and you see that the probability for the normal discriminator comes from 1 to 0, right? But for the VGAN discriminator, it goes from infinity minus to infinity plus. So that's kind of one first really interesting stuff here. by the way, the VGAN is Wasserstein-GAN, so let me write down. Wasserstein-GAN, and this is basically, this is fancy word, and the paper, if I remember correctly, also was not that great written, but basically this is fancy word for the earth movers distance loss. So earth movers distance is a really simple concept. Basically, this is alternative to KL, etc. So alternative to kind of measure the difference between two different probability distributions, or any two different kind of vectors, or it might be alternative to KL, to PLDA, or any kind of metrics like that. So again, this is more related to the metric learning. Basically, the loss itself is not any more probability. So they are not really probabilities. They are more about the similarities or the measurement of distance between the two types of distributions. So that is that. But let's keep digging, so you will start hopefully to get it better. So the earth mover's distance itself, again, one visual representation which I found was this one. So there, if you imagine that you have distributions of, for example, in this case, you have a blue distribution and red distribution, and they're just like holes. Basically, you want to put the dirt, like the red dirt, inside the blue holes, and you want to measure how much work does it take for you to put the holes from one side to another side. I mean, from the piles to the holes, right? So, and then you can do this process iteratively, like one step at a time, and calculate the distances and sum all of them together. And you also can formalize that as using the some of the earth movers distance formulas. So there is one not really clear in my opinion. There is another one which is also not really clear in my opinion. But I found actually really nice explanation in I think it was in Stack Overflow, where some person just go on step by step how to move basically dirt with shovels, quote unquote, from A distribution to the B distribution. So you use this, basically this equation, which I think makes much more sense than the other ones. So this one I think is the best one. So and then you iteratively just move the distance from one to another. So you start here, there is, to explain this equation, so on the one side you have the A, so in this row you have the B's, so basically it's not that clear, maybe you're right. So these guys are B's, all of these, and on the other side those are A's, basically. And then you do this step by step, and at the end you come up with that it will take 4 shovels to move all of the dirt from A to the B. So that is kind of in the like broad sense the earth movers distances. So you can do a lot of things with those distances. They are kind of statistically much better kind of approximation than just using like Euclidean or cosine distance directly between two distributions. So basically this is one way how to measure the distance, right, between two distributions. So that part is fine. Then we go again, so this is very similar with the DCGAN and the GAN itself. So you have the idea of using earth movers distance for GANs for determining like is this samples real or fake, and how far the real samples are from the fake samples. So this is the basic idea, right? So, but the reality is a little bit different again. So it's very good that they give the equations actually in how they use it at the end, because at the end, it's just IDEA, basically. In my opinion, from what I see here, is that earth movers or distance or WGAN is just like that part, the Wasserstein part is just IDEA, what they try to apply in their model for the loss function, but it's not directly one-to-one equation. So here, basically, the IDEA is coming mainly inside the discriminator part, as it was in the previous slide in the chart. So you see that what's happening here, and again, there are a few very tricky stuff happening here. So first of all, FW, that is the discriminator. So FV, that is discriminator, and G is GAN, generator, right? So that is fine. So here, in this part of equation, we see something really strange, which means that in this part of equation, I'm just doing so the discriminator takes X minus the discriminator takes G takes Z, and then I'm using the mean value of all of this, right? And then I'm using this as my loss function. So you see already that there is no minimum for this function. It can go to infinity. So that is one thing. The other thing, which is really nasty, I think, in this equation, because I don't know why would they do this. So you see here, they have plus sign, and here you have a minus sign. Normally, all of these optimization problems just go in one direction. So you would even min-max, in that case, it didn't make sense, but here it's even more confusing. So basically, this part is normal optimizer for the PyTorch. This part is not normal optimizer. This is opposite. So to make it opposite, we just need to add minus sign in front, basically. So let me do that. So minus sign in front. Let me emphasize that. So here, so then it would go in the correct direction. So that's one thing. Just to reiterate, if I go back here, a few slides here, so the discriminator of X should produce minus infinity if this is a real, and should produce plus infinity if this is a fake. So that, and they call it actually score or something like that. Basically, this is not any more probabilities. This is kind of more like in the terms of piles, like piles of dirt or scores or whatever. So you have this thing, and you already see that all of this kind of complex equation with iterations here in earth movers distance is just reduced down to really simple one minus other equation, and there are some repetitions of this. Like they say that they repeated 5 times, you can change it, whatever. So basically this is the loss discriminator. And for the generator loss, this is, I think, almost the same as before. It's not probability, it's just doing the opposite of what we are doing there. So this will be then D, G, Z. So loss of this thing. And I think it even gets more confusing here. So this is loss D, this is loss G. Let me write it like that here. So the minus sign. And of course, if I just would replace the minus sign, right? So basically what would happen here is that, okay, maybe I should drop the mean like that. So it would just replace it the other way around. So would it replace it the other way around? So DG, okay, there is a minus sign in front here. I didn't notice that. Minus, and here if I replace the other way around, DZ minus DX. So now you see, we have two opposing forces here. So this one wants to go to the, infinity, and this one want to go to minus infinity. And this one wants to go to also to the minus infinity. So that is what we have here. And the final thing is, if everything can go to the infinities, then this is bad, because it might quickly just blow up all of our model, right? So to solve this, they propose to use this hack here, which is gradient clipping. So it means that I want not to have too large gradients so that I can control my process and stop it maybe after 100 epochs before everything blows up. So that is basically in short terms how the Wasserstein GAN works. There, as you see already, there are quite a few strange issues with this model, but at the same time, the convergence you will see is it's not really kind of convergence, but the way how the model trains is much better because both loss G and loss D will tend to go to the same direction, and they would kind of try to converge on some arbitrary axis downwards direction. So that's why it works better. Okay, so that is that. Let me just check one quickly. Is it clear? Plus, minus. If something is not clear, you can try to write what exactly is not clear here, and I can explain, and then we will code it just briefly. We will not need to change the models. We will just need to change the loss functions a little bit. So what we just did, we replaced the probabilistic approach of probability being real or fake to some kind of score which can go from minus infinity to plus infinity, just to make sure that the loss function kind of converges better. And also avoids the mode collapse. So the mode collapse is one of the hypotheses for the Wasserstein GAN, is that it happens when the gradients get stuck in in some locality. So I'm waiting for some confirmation. Okay, great. Thank you, Gins. So I see one confirmation. Let's go to the code then. So to code this thing, my suggestion is following. We should copy the template. So let's copy the template from the DCGAN to VGAN. Copy, paste. I will call this WGAN live. WGAN live. Wasserstein GAN live. So, okay. So what we need to do, first of all, because there were actually those few loops there, I think those loops kind of simulate the Earth mover's distance as well. Maybe I'm wrong, but I think that they do that. So I think in that sense, if we have two loops, then it might be reasonable to actually update the gradient more often. Let me see. Yeah, so at least from the equation that I have on the Jamboard, they do update it more often. So what instead we can do, what is this? So this is WGAN live. Okay, I don't know what I was doing before. So anyway, so what we can do is to copy the optimizer. So we have the optimizer here. So let's split the optimizer in two optimizers. By the way, you can do the same thing for all sorts of tasks, not only for the GANs. So let's split out the D optimizer and the G optimizer. So I will have the G optimizer and D optimizer. So that is the only change necessary here. And the reason for this is because I want to be able to update gradient independently between G and D. And for the first task that I showed you for the simple DCGAN, it was really nice that you can combine the loss functions in one update call. You could actually do this also for the Wasserstein GAN, but I don't think it will be that stable. It's already not. So the equation itself goes to infinity, so that's not cool at all. So see here. So we have the generator part. So the generator part will be really simple stuff here, so there's almost nothing to change. So the generator part, the only thing we need to change here is to try to push this to infinity, to minus infinity basically. So please push this to the minus infinity gen, like that. So this will be then optimizer, oh no, not optimizer, but loss G backward. So I will do the backward pass immediately here, and then I will do the optimizer G step, optimizer G clear 0 gradient, right? Let me check, GD, right, this is fine. So yeah, so this is the loss function part here, so pushing to the infinity. Then down here I will delete all of this loss optimizer step grad, because this is just for the statistics. This is not for actually updating the bottom part. So then the actual updating the discriminator. So here we'll have for n in range, how many times we want to update it. Originally in the paper they use 5 times, we will use 2 times or 3 or 4. You can change whatever, make this a hyperparameter. So this part, again nothing changes here except the loss function. So now the loss is actually then the loss D equals, so this will be, these guys will be just, so let me see what was created in that equation in slide number 9. So in slide number 9 they sum it before. Just a second, so let's write it down. In slide number 9, so they first do the torch mean of the y fake minus torch mean. In the original equation, this is the other way around, right? But the original equation, they also add the secret minus sign in front, so that's why it's another way around. So, but it should be, this is correct basically. So then loss backward. Then we need to clip the gradient, which is this thing. What should I do? Torch and n utils clip grad norm, this function with this sign. Model D parameters, max norm, again they use 1e minus 2, norm type, which is either L1 or L2, then optimizer D step, optimizer 0 grad, right? So this is what we have here. Okay, this should be done for the loss function. I will drop this also to the Jamboard. And then there is one more thing which I need to change, is that in the model itself do not need to return sigmoid at the end for discriminator. So if I go to the discriminator now, where is the discriminator? At the end, in discriminator, we don't need any more sigmoid. So no sigmoid at the end here. We will also update this part. Because we want to go to the infinity, sigmoid will not allow us to do that. No sigmoid. So that part. So no sigmoid there. Right, so I think so far everything should be fine. So I'm uploading this stuff to the server, trying to run it. So this is, oh no, I updated DCGAN live. Seriously. I updated wrong template. Okay, I will then need to rename them. This is, hopefully you updated the correct template. So now it's training. I'm just thinking maybe I did something wrong because I see that the G have interesting values. Torch mean Y generated seems to be right. Okay, let's see. Maybe it is okay already. So let's see what is my outputs. So the outputs look good, but I'm not really sure that the loss function is working correctly. I will need to check it. So meld. I will check it, what's happening here. So maybe I missed something. So I want the real to go to infinity, which is correct. Seems to be okay, I think. Param true, param was param false, fine. Okay, seems to be okay. At least I don't see any serious problems with it. Okay, nice. Now it started to converge. So I guess it went up and then now it starts going down. Yeah, so great. It just took a little bit longer. That's why I was, you know, like I was starting to get worried, but it works great. So, okay, so let me then share this slide. Slide number 11. Okay, where is the image? Okay, so you see now the way how it converges, it's really interesting. So it's again similar to reinforcement learning, but now it like just goes in the same direction with some variants, right? And the outputs are really crisp and nice. And basically, the initial part was a little bit tricky, but then it starts going down, and it should go like for a long time, and then you just so like depending on how good are the outputs, you would stop it. So again, this is an active research topic based on like what means good output. You know, here it's not that easy to determine. And yeah, I think that's about it for today. So you can create really cool GANs. I will probably make for the homework the some kind of face maybe or cars data set that you could try out using the VGAN with some additional updates. I will share one very good small paper where there are combined all of the best updates to do for the GANs so that they would work better. So you'll try to do that part as well. So that's about it for today. I think it was really interesting. So next time we will start working with style transfer. We'll start working probably with the, what was the name of that model? DTN-GAN, Domain Transfer GAN. And then either we will have another session where we will work with cycle GAN, or you will be able to do that at home, so we will see that. But basically, next week we will work on the style transfer GANs, where this deep metric learning stuff will be even more more similar to what we did before, where you will try to actually control the z, because now the z, controlling on the z is only in terms of the probability distribution, right? In the very beginning and also in the code, we have this Gaussian distribution. That is the only way how we control the z, but there are better ways how to control the z. So we will look at those in the following sessions. So that's it for today. Bye-bye.